All right, hello everyone, and welcome back to this little three-part mini-series on stars. So last week we talked about how do we form stars, how are stars born, and not just the movie starring Lady Gaga and Bradley Cooper. Um, but today we're going to talk about how stars spend the majority of their lives in this talk on star stuff. So tonight's quote is a very good one of Neil Gaiman in his novel Stardust. A philosopher once asked, "Are we human because we gaze at the stars, or do we gaze at them because we are human?" Pointless, really. Do the stars gaze back? Now that's a question. So, when it comes to the lives of stars, the defining characteristic of a star is its mass. Remember from 2 weeks ago that the mass of a main sequence star pretty much determines their luminosity and how long they're going to live on the main sequence. Because stars with larger masses on the main sequence have larger luminosities, they're going to shine more brilliantly than the ones with small masses. Small masses are generally pretty dim. And that means since they have much greater luminosities, they've got to be producing this energy. They've got to be releasing that energy through fusion at a higher rate. And they have this higher fusion rate because as they form from gravitational contracting, that molecular cloud is going to collapse in on itself, fragment into a bunch of smaller clouds. Each of those clouds is going to gravitationally contract, transforming gravitational potential energy into thermal energy. High mass stars, as they do that, are going to release more energy and heat up more rapidly, reaching the temperatures necessary for fusion much earlier, 10 million Kelvin inside the core of the star. And so they're going to be releasing energy at a much higher rate. And with that increased rate, they will consume their hydrogen much more rapidly, giving them much shorter lifetimes. So bluer high mass stars live for around 10 million years, on the order of 10 million years, which is very, very short on a cosmological timescale. Intermediate, low mass stars like our own sun, nice yellow white star, will live for about 10 billion years, 10 giga years. And even lower mass, red dwarfs are going to live for hundreds of billions of years. If there was a red dwarf that was created at the beginning of the universe, it is still around today. It has not died out yet. A star's mass will also determine what happens to the star once it does run out of hydrogen. So if the star is much more massive than our sun, then it will continue to fuse heavier and heavier elements, helium, carbon, oxygen, all the way up to iron. And we'll talk about that as we go through this talk. If it's too low, once it runs out of hydrogen, it's pretty much done. It's not going to do anything else. And even after all the fusion is done and the star has gone and died, the initial mass of a star, what it started out with, will determine what happens to it when it dies, whether it's just going to be a white dwarf, become a neutron star, or even a black hole. We'll talk about all of that in next week when we talk about the stellar graveyard. So for this talk, we're going to split up stellar masses into 3 different mass ranges. We'll have low mass stars. Those are stars born with less than about 2 times the mass of our sun. Intermediate mass stars, those with masses between 2 and 8 times the mass of our sun. And high mass stars, those with masses greater than 8 solar masses. So we'll focus primarily on the dramatic differences between low mass and high mass stars. The life stages of intermediate mass stars are pretty similar to the stages of high mass stars until the very ends of their lives. So we'll sort of include them in our discussion of high mass stars. And you might wonder how we know anything at all about these things, since we certainly don't even live for the shortest timescales of stars. We don't live for 10 million years. We've been on this planet for maybe 200,000. And certainly we have not spent all of that time with the technology we have today. So how do we know anything about what these stars do? Well, thankfully, there's a lot of stars in the universe, all at various points in their lifetime. So we can see sort of a snapshot of different stars of the same mass of stars at different points in its lifetime. We also have computer modeling. We have equations that very accurately reproduce and allow us to model what happens to these stars as they grow older. So through somewhat careful observations, but primarily through models, we're able to get a good sense of what these stars are doing. There are always still some questions, and there are always still some very weird stars, but for the most part, we think we've got it figured out here. Okay, let's start with low mass stars. So according to our little breakdown of low, intermediate, and high mass stars, technically the sun is a low mass star. And all low mass stars are going to spend the majority of their lifetime on the main sequence, fusing hydrogen into helium via the proton-proton chain. We talked about this several weeks ago when we talked about the sun, but if you need a reminder, the right image is the predominant chain reaction for the proton-proton chain, where you take two hydrogen nuclei, so essentially just two protons, smash them together to get hydrogen 2, that's deuterium. Then you hit it with another hydrogen nucleus to get helium 3, and you do that twice. So at the end, you have two helium 3 nuclei, two protons, one neutron. Those two helium 3 nuclei smash together to give you a helium 4 nucleus and a return of two hydrogen nuclei. So you need 4 total, a net of 4 hydrogen nuclei to form one helium nucleus. That is the predominant way of which low mass stars are generating their energy in their cores. They're not doing it through any other mechanisms, really, and that's all they're going to do for most of their life. And this energy will escape the core. We talked about these two methods when we talked about the sun, through radiative diffusion, where photons of light are essentially free streaming outwards from the core, hitting an atom, a nucleus every now and then, and maybe being redirected, but essentially just bouncing around inside the core until they reach the convection zone, where it's become more efficient to instead do this kind of bulk transfer, where hot material rises, cools at the top, and then sinks to be heated again, just like a pot of boiling water on your stove. The difference here is between the masses of the stars also determines the depth of their convection zone, where very low mass stars, we're talking less than a half of a solar mass, have convection zones extending all the way to their cores with no radiative zones. Our sun is a low mass star, not very low, but it's just a normal low mass star. And so it has a radiative zone around its core and convection zones up towards the surface. Meanwhile, as you get to slightly higher masses, that it flips. The radiative zone is up towards the surface and the convection zone is much more closer to the core. That's the only difference there, but they're all going to be using the proton-proton chain to generate energy. Now, the depth of the convection zone does determine whether or not a star has activity very similar to the sunspots on our sun, that solar activity on our sun. Remember, those come about through the twisting of magnetic field lines, because since the equator rotates faster than the poles in the sun, those magnetic field lines are going to get twisted due to convection and that rotation. And so there's going to be a lot of activity on stars with very strong convection, like very low mass stars that are just completely convection dominated. And so if they happen to be rotating very fast, then that actually makes them incredibly active. All those magnetic field lines are being twisted and snapped and shooting out tons and tons of energy, producing, surprisingly, a lot of X-ray light, more than all of the X-ray light it would produce through other means. These stars are called flare stars, and you can imagine that life on a planet around a flare star would be very, very, very difficult. The right is an artist's renditioning of a known flare star. We've discovered these. But aside from perhaps these flares and maybe some other surface activities, most of these low mass stars, these red dwarfs, their lives are very uneventful. They're just going to continually be fusing hydrogen for hundreds and hundreds of billions of years, slowly increasing in temperature and luminosity as it ages, for the same reasons that we talked about for the sun. So the fusion in the core of a low mass star reduces the number of independent particles in the sun, because we're taking 4 hydrogen nuclei, 4 protons, and changing it into just 1 helium nucleus. And so so as the number of particles drops, the core will shrink a bit and heat up in order to keep the balance of pressure and gravity in the core. And that slight but continual rise in the core temperature will raise the fusion rate, therefore the luminosity of the star as it ages. So they're always sort of getting a little hotter, a little brighter, but very slowly. Now, where we start to see some radical changes is when we've run out of hydrogen in the core of the star. When that happens, the core is going to shrink, because suddenly it's not generating enough thermal pressure, not releasing enough energy to fight off the collapse of gravity. But somewhat confusingly, somewhat surprisingly, the core is shrinking, but the outer layers are going to be expanding. At first, we'll talk about why they're expanding in a moment. At first, you can see here, the red circle on this HR diagram is the sun. So let's get our bearings again. So on the left axis, on the left vertical axis, is the luminosity of the star, how bright it is. So really bright up top, really dim down below. On the horizontal axis is temperature in reverse. So really hot towards the left, relatively cold towards the right. And you can easily see the main sequence here, the giant group here, and then the white dwarfs below the main sequence. This red dot is where the sun is currently at 1 solar luminosity at a temperature of about 6,000 Kelvin. And this red line is the path it will take through the HR diagram as it ages. So at first, the star is going to move horizontally towards the right as it expands. So it's not increasing in luminosity very much as it's doing this, just decreasing in temperature. The outer layers are cooling off to become a subgiant. And then, as the expansion continues, the star's luminosity will increase, as well as the surface temperature decreasing, making it become a red giant. This happens over a time period of around 1 billion years. So it's not going to happen, immediately. We'll talk about what red giants are in a moment. So why is it expanding? The core is contracting, but why is the outer layers expanding? Well, towards the end of a star's main sequence lifetime, the core is going to be almost entirely helium, just sitting there inert. The helium is not being fused yet. The temperatures are not high enough to fuse helium yet. However, there's still tons of hydrogen in the star, just not in the core. There's hydrogen surrounding the core on all sides. So as gravity shrinks, as gravity compresses that inert helium core, which I've colored here in blue, and we've got a surrounding shell of hydrogen that's also being compressed, the hydrogen shell, which wasn't yet at the temperature for hydrogen fusion, will eventually reach that temperature and we'll have hydrogen shell fusion. And in fact, this shell, colored here in red, will be hot enough for hydrogen fusion to go at an even faster rate than it used to happen in the core. So that's going to build up a lot of thermal pressure to counteract that force of gravity on the outer layers, which will actually push the surface outward and cause the star to expand, thus making it a red giant. However, the shell can't do anything to what's inside of it, that helium core. So that's why the core is shrinking, pulling the shell with it, but the shell is generating so much energy that it's actually pushing the outer layers of the star away, expanding them to become a red giant. Now, once that core reaches about 100 million Kelvin, it used to be at 10 million, so we've gone up another order of magnitude. Here we can finally start helium fusion. This is often called the triple alpha process because for historical reasons, before we knew that they were just helium nuclei, we used to have things called alpha particles that happen in reactions. And there's 3 helium nuclei in this reaction, so it's the triple alpha process. So energy is released because, so the reaction goes, 2 helium-4 nuclei collide together to form beryllium-8. And then beryllium-8 gets smacked with another helium nucleus to form carbon-12. And in each of those 2 reactions, some energy is released. And energy is released because carbon-12 has a slightly lower mass than the combined mass of those 3 helium-4 nuclei. However, it's still not enough to stave off the collapse of gravity. There's still not enough thermal pressure, not enough energy being released to counteract gravity. Instead, what happens is that degeneracy pressure is going to fight against gravity. The electrons can't be too close to each other. Once again, it's the Pauli exclusion principle. Go back and watch the talk on particle physics on quantum mechanics if you need a refresher. Pauli exclusion principle says you can't put too many electrons in the same spot because they don't want to occupy the same spot. It's like asking me to also be in the same physical space as someone else. Not next to them, but inhabiting the same physical dimensions. That would be very bad. Sounds like a Star Trek episode. So that degeneracy pressure is going to stave off gravity. So therefore, because the thermal pressure is continually building up, that temperature is just going to keep increasing until all that pent up energy is released in one kind of big boom known as a helium flash. And the core temperature will rise to reach that 100 million Kelvin in a matter of seconds. You don't actually notice this on the outside of the star. You won't notice the star, suddenly brighten really fast. I'm not going to do that, but it will. This will happen in a matter of seconds. So here's another little Here's another little HR diagram where we've exhausted all the hydrogen in the core on the main sequence. So it's forming a subgiant and then the red giant as hydrogen fusion moves into a hydrogen shell around an inert core of helium. And then right up here at the top, it's very bright. We'll see a helium flash. And then once that helium fusion begins, the core and the shell will be expanded along with the outer layers. Because finally there's fusion that can stave off the collapse of gravity after that helium flash. And this will lower the temperature, reducing the fusion rate, which also reduces the luminosity and shrinks the star somewhat. So we'll get all the way up here to the helium flash, and then we'll immediately increase the temperature, the surface temperature, lowering the luminosity, and it will be on the horizontal branch. And that's happening as the star contracts somewhat. So it becomes a yellow-white helium core fusion star sitting on the horizontal branch. When we look at clusters of stars, we can see all of the things we just talked about. This is the HR diagram for stars in the Great Hercules cluster. It's a globular cluster. So down here at the bottom, where most of the black points are, those are stars sitting on the main sequence. But you can see this main sequence turn off, which once again, if you remember, that could tell us the age of the cluster. And you can see we've got subgiants and then red giants on the RGB, the red giant branch. And up here at the top, those are stars that are about to have their helium flash. And once they do, they'll turn back down here and get stuck on the HB, the horizontal branch, where they'll be doing helium fusion. They're slightly hotter, slightly dimmer. They're doing helium fusion. So we can see all of that happening in the HR diagrams of so many star clusters, especially the older ones that have had time for stars to evolve off of the main sequence. But eventually, even the helium at the core is going to run out, which will once again cause the outer layers to expand, this time not caused by a hydrogen fusing shell around the core, but instead a helium shell around an inert carbon core. The hydrogen shell is still there, but it's not producing as much energy as the helium shell. And once again, the fusion rate will increase as the shells and the core contract. But this time, equilibrium will never be reached. So instead, we're not going to give this smooth expansion. We're going to get thermal pulses every few thousand years, where the star is actually going to, expand and contract rapidly. At this stage, the giant star will only have a very tenuous grasp on its outer layers. So this star might be losing a sun's worth of matter every 100,000 years, expanding away in some very, very strong stellar winds and some other processes as well. And those outer layers will slowly expand away, leaving behind an exposed carbon-rich core called a white dwarf, which that high-intensity light, because white dwarfs are very hot, it will ionize the gas that's just escaped from the star, making it glow as a planetary nebula. Now, planets are not forming in a planetary nebula. It's named that for, once again, historical reasons, because that's what it looked like in the telescopes at the time. But these are actually the dying remnants of stars. So what you'll end up getting are stuff like this, beautiful, beautiful planetary nebulae, like the Helix Nebula on the right, where you can actually see the remaining core. It's the white dot at the center. That is the core of the star that's blown off all of this gas. And the Butterfly Nebula, where the star is at the center of those two wings of the butterfly. This is what we get when a low mass star dies. We get a planetary nebula. The nebula will disperse in about 100,000 years, leaving behind the white dwarf. And we will talk about white dwarfs in great detail next week. But they are very, very hot because they are essentially the exposed core of a star. And they haven't had much time to cool yet. Now, they're not going to be doing fusion. They're just going to be slowly radiating away their heat until they form a hypothetical black dwarf. We have not seen a black dwarf. We don't know if they exist yet. The universe is still too young enough for white dwarfs to have cooled completely. But this is what happens to a low mass star. So here's just a summary of what's happening here. Here we've got a star, a low mass star on the sequence. This is actually a one solar mass star. So this is what the sun is going to do. As it runs out of hydrogen, it will move on to the subgiant branch and start to do hydrogen fusion around the inert helium core, expanding the outer layers, becoming a red giant on the red giant branch, reaching a peak up here where we'll have finally built up enough temperature in the inner core to start helium fusion in an instant in the helium flash, and we'll rapidly move back down here onto the horizontal branch as a helium fusing star. There's no dark red line connecting because that happens really in the matter of seconds, not on the order of millions of years, like most of these changes happen. It will slowly move up and it will go through some thermal pulses on the asymptotic giant branch. We're not really going to be talking about what that is. And as it blows off its outer layers, it will rapidly come down here below the main sequence to become a white dwarf surrounded by a planetary nebula. Here, this bottom left is a little animation showing what the sun will go through. So here, this little yellow dot is where the sun is currently. Let's press play here. Oops, there you go. So the sun's going to move up, become a subgiant, then a red giant, and then on very, very fast time scales, become a white dwarf. There you go. A lot of those stages happen very, very fast. A star, regardless of its mass, is going to spend most of its time on the main sequence. All these other things that are happening on much more rapid time scales. Now let's talk about a high mass star. So in high mass stars, on the main sequence, gravity is able to compress the core into higher temperatures, which makes it possible for protons to slam into heavier nuclei, such as carbon, oxygen, and nitrogen, if they exist even in small amounts in the core, as well as other protons. So it's actually, they're not going to be fusing hydrogen through the proton-proton chain. They are going to be fusing hydrogen by using the carbon, nitrogen, and oxygen nuclei as catalysts to allow it to happen more rapidly. This is known as the carbon, nitrogen, oxygen cycle, or the CNO cycle for short. So here's our little wheel for the CNO cycle. We'll start at step 1. Hydrogen hits a carbon nucleus to form nitrogen-13. That nitrogen-13 decays into carbon-13, which is hit by another hydrogen to form nitrogen-14, which is hit by another hydrogen to become oxygen-15, which decays into nitrogen-15, which is hit by another hydrogen to form helium-4 and carbon-12. And then you repeat the entire process. Now, the saying it's using carbon, nitrogen, oxygen as these catalysts, but it's the same overall reaction. 4 hydrogen nuclei are coming together to form one helium-4 nucleus. Nothing is happening to the carbon, nitrogen, and oxygen. They're just there to help it along. They're not getting used up or anything. They're not even being fused together yet. It's still hydrogen fusion, just using other nuclei as catalysts. Because the CNO cycle is so efficient and so rapidly fusing hydrogen, high-mass stars don't live very long on the main sequence. They maybe live for on the order of a few million years, maybe 10 million at most, 100 million. They're not going to be sticking around for long. So that's why we know that every high-mass star created at the beginning of the universe died out a very long time ago. All of the high-mass stars that exist today were essentially created yesterday on the terms of universe timescales. So they're not going to live very long in the main sequence. In fact, rapidly, the hydrogen is going to run out in the core. And essentially the same things are going to happen as in the low mass star that we discussed, but just on much faster timescales. So once again, a hydrogen fusing shell is going to develop around an inert core of helium. And that core will contract until the helium can reach the temperatures necessary to do helium fusion through the triple alpha process, fusing helium into carbon. Now, for stars that are greater than 2 times the mass of our sun, there is no helium flash. And this helium fusion just starts gradually. We don't need to build up temperatures and pressures to start helium fusion. It will just happen gradually. And this helium fusion actually happens so rapidly that after only 100,000 years, the core will shrink again, temperatures will rise, and we'll get a helium fusing shell around an inert carbon core and a hydrogen fusing shell on the outside. Now, intermediate mass stars don't go beyond this point. They'll have a inert carbon core, helium shell, hydrogen shell, and then just some hydrogen floating around in the outer layers. So, and they won't get past this point. They'll just blow off their outer layers and become a white dwarfs. But the really high mass stars, greater than 8 solar masses, will continue on from here. So, for example, here's a star that is, this little animation will show a star that's about 5 times the mass of our sun. It will only live for just about 140 million years. It's a very, very short time scale. You can probably barely see the blue dot, but right where my mouse is where it's going to start off. Here you can see it's going to move off the main sequence relatively fast, and it's all going to be over in a blink of an eye. And there you go. That's it. They don't live very long. All right, but those really high mass stars, those are going to go keep fusing stuff into heavier and heavier elements. So low mass stars can't do this because the degeneracy pressure will keep them from reaching the temperatures that are necessary to do higher element fusion. But high mass stars don't have that problem. So the simplest fusion, there's tons of different fusion processes, but the simplest one to at least conceptually understand is called helium capture reactions, where we take a heavy element, add helium-4 to get a heavier element. So for example, carbon-12 plus helium-4 gets you oxygen-16. Oxygen-16 plus helium-4 gets you neon-20. Neon 20 plus helium 4 gets you magnesium 24. Essentially, adding 4 to this number, increasing, moving further up the periodic table. And so they'll do this in their core successively. And at high enough temperatures, you don't even need helium. You just fuse 2 heavy elements together. So carbon 12 plus oxygen 16 gives you silicon 28. Oxygen 16 plus oxygen 16 gives you sulfur 31 and a return of a hydrogen. Silicon 28 plus silicon 28 gets you iron 56. And each time the core depletes the element that's fusing, the core will contract, heats up, starting to fuse the next element while a new shell ignites around the core. So if you could do a cross section of a very high mass star, it actually would sort of look like an onion, where we've got just shells doing increasingly heavier element fusion, hydrogen around a helium, around a carbon, around neon, around oxygen, around silicon, with an iron core at the center. So they're fusing all of the heavy elements of the universe. We really have high mass stars to thank for a lot of this. But despite all of this stuff happening in the interior, despite all this new fusion happening, the appearance of a high mass star doesn't change that rapidly. Every time the core fusion ceases, fusion in the shells will intensify and the star expands, cooling it slightly, so they'll move to the right on an HR diagram. And each time the core fusion starts, those outer layers will contract, heating up, but the star's luminosity will remain pretty much the same. So here we've got a bunch of different evolutionary tracks. So let's just look at the 10 solar mass star here on the main sequence. So it'll move to be a subgiant as it fuses hydrogen to helium. Then once it's run out of that, it's going to become a supergiant and start to fuse heavier and heavier elements in its core, kind of doing a little zigzag on the HR diagram. And you can see down here, I've compiled numbers for how long a 20 solar mass star will spend doing each of these different types of fusion. So a 20 solar mass star will sit on the main sequence for 10 million years, fusing hydrogen into helium. Then fusing helium, it'll take about 1 million years. Fusing carbon, about 1,000 years. Fusing oxygen, just a year. Silicon, a week. Iron, less than a day. So all these other fusion processes are happening. It only takes a very short amount of time for it to move on to the next step. So if you remember last year, at the beginning of last year, there was a lot of news about what the heck was going on with Betelgeuse. Is Betelgeuse about to explode? Is about to go supernova or not? Because it was varying in brightness, it was decreasing in brightness. Essentially, if Betelgeuse is fusing iron right now, then oh my gosh, look out at the sky tonight because it's going to explode soon. We don't know at what stage it is at in its lifetime, what fusion it's going on, but if it's fusing iron right now, then yeah, tonight it's going to explode because it's not going to live very long. And the reason it's not going to live very long, oh, here's a little movie for a very high mass star moving off the main sequence and evolving. Yep, everything happens very fast for these stars. So the reason once it gets to iron, it's going to explode is because iron is a very unique element. It is the one element from which it is not at all possible to generate any nuclear energy. The lighter elements, fusion is going to release energy. Hydrogen to helium fusion, we're releasing energy. Even helium to carbon, carbon to oxygen, we're all releasing energy. Heavier elements than iron, fusion is not going to do anything, but fission is. Uranium fission, which is what happens in our nuclear reactors here on Earth, that releases energy. Breaking down the heavy elements into lighter elements releases the energy. And this all happens because each of those reactions, say hydrogen to helium or uranium to what? Thorium or whatever happens in nuclear reactors. Those releases energy because the product has a lower mass per nuclear particle than what you're starting out with. So helium-4 has a lower mass per nuclear particle than hydrogen. And similarly for carbon fusion and uranium fission and so on. Iron has the lowest mass per nuclear particle of every nuclei. And so it can't release any energy by either fusion or fission. If you want to do anything with iron, you've got to put energy into it. So that means that iron is just going to pile up in the core until not even degeneracy pressure can support the star anymore. And once that happens, what do you get? You get an explosion. You get a supernova. So here's what happens in a supernova explosion. This all happens very, very rapidly. So once gravity pushes the electrons of the core beyond the quantum mechanical limit of degeneracy pressure, they disappear essentially. They combine with protons to form neutrons. And neutrons neutrons also have a degeneracy pressure, but it hasn't kicked in yet. So that means gravity has free reign. And so gravity is actually going to contract rapidly in a fraction of a second. We'll go from an iron core with the mass of our sun and the size of the Earth, will collapse into a ball of neutrons only a few kilometers across, halting only because neutron degeneracy pressure has kicked in. And that gravitational relapse releases an enormous amount of energy that essentially goes into rapidly expanding the star's outer layers in this giant explosion, which we call a supernova, which leaves behind a neutron star in the process. So here's a little animation of that supernova. Blindingly bright, leaving behind a supernova remnant and a neutron star at the core. So we have seen supernovae in our own galaxy. So there's a few very good historical supernovae. The one happened in the year 1054, and the remnant that left behind we now know as the very well-known Crab Nebula, also known as Messier 1, the first entry in Charles Messier's catalog. One happened in the year 1006. You can see the X-ray light there in the middle. Another one was discovered by Tycho Brahe. He saw it in 1572. We haven't seen a supernova in our galaxy in almost 400 years. We're overdue for one. And maybe one has happened. There's a whole other side of the galaxy that we can't see due to all the dust in the way. So maybe one has happened over there where we can't see it. But we are certainly overdue for one. We have seen supernovae in other galaxies as well. So on the left was a very recent one in 1987. Happened in the Large Magellanic Cloud. So this big complex up here is the Tarantula Nebula. And you can see the arrows pointing to the star before it went supernova, and then here's the star after it went supernova. Completely, almost equivalent to the amount of light just in that Tarantula Nebula. Here is a galaxy that I study, the Pinwheel Galaxy, Messier 101. There's a supernova in it in 2011, where this arrow is once again pointing towards the star that's about to explode. And there it is. Supernovae release tons and tons of light, light equivalent almost to an entire galaxy. It does often outshine the galaxy that it is in. These are truly cataclysmic explosions. So we will talk about the remnants, what is left behind after a supernova next week. But these are really big events here. And thanks to all of the things we've talked about tonight, we have all of the elements that we see in the universe. Now, some of them are man-made. These are the man-made elements. Stars don't produce these. Technetium 43, I don't know what PM is, but 61, and then anything 95 and higher. Those are all man-made. But every other element is created in a star. So hydrogen, helium, lithium, a lot of it is produced during the Big Bang. But heavier elements, so low mass stars create all of these. Carbon, nitrogen, we're a carbon-based life. Without low mass stars exploding, we wouldn't have carbon. Many of these other elements go into so much of our technology. High mass stars create all the other ones. Oxygen that we breathe, neon that goes into our lights, aluminum, silicon, sulfur, chlorine that goes in our pools, sodium. So we have salt. potassium, calcium, all of those created in high mass stars. Now, a lot of the other ones were created through merging neutron stars, which only recently have we had definitive evidence of. So all the uranium, neptunium, plutonium, gold, silver, mercury, I think, all of that created in merging neutron stars. There's even some that were created during white dwarfs that are exploding. Iron, titanium, cobalt, nickel, copper, zinc, all those elements that go into so much for technology. And then beryllium and boron are the two odd ones out that are actually produced through cosmic rays. Those are very hard to produce, apparently. But we get all of this from essentially exploding stars. So without those stars, we certainly would not be around to even talk about them. All right, as always, we're doing astronomy. You can actually go outside tonight or in the coming days and look at what we're talking about. So I wanted to give you a little orientation to some of the things you can see in the night sky. So, all right, so let's say you want to find some stars. Well, you should be able to identify the Big Dipper. So if you go outside at night, look in the northwestern skies, you should be able to see the Big Dipper there. That is part of the constellation of Ursa Major. The Big Dipper is not the constellation. The Big Dipper is called an asterism. Ursa Major is the defined constellation. And if you look at the star at the end of the handle, that's called Alkaid. I believe it's a main sequence star. Then you can follow the curve of the handle and you arc to Arcturus. That's how you remember it. You arc to Arcturus, a red giant, I think, in the constellation of Bootes, the dog hunter, I believe. And then to find another star, you speed on to Spica, a straight line down to Spica in the constellation of Virgo. So you can find some stars that way. If you want to find the northern star, Polaris, once again, you can start from just finding the Big Dipper. There's the Big Dipper again in the northwestern skies tonight. And if you look at the two stars at the end of the cup of the Big Dipper, Merak and Dubhe, and extend this 5 more times, you should be able to find Polaris. And once you find Polaris, you can find the Little Dipper, Ursa Minor. There is no extension to Ursa Minor. The Little Dipper is the constellation. And then another asterism that is easily visible in the summer skies, if you look almost straight up in the eastern skies, and you can probably find one of these 3 bright stars. Let's say you find Altair in the constellation of Aquila the Eagle. Then you can create a triangle with the other 2 bright stars, Deneb in Cygnus the Swan, and Vega in Lyra the Lyre. You can find the summer triangle. That's what it's called. It's not a constellation. It's just an asterism, but a very handy one. So I encourage you to go outside tonight, look up in the night sky and see what stars you can find, what constellations you can identify. See if you can find the summer triangle. Maybe you could arc to Arcturus and speed on to Spica. Find Polaris. Just learning maybe 20 of the 88 constellations can make the night sky seem as familiar as your own neighborhood. So I definitely encourage you to go do this tonight or in the coming night, if of course the weather lets you. So that is it for tonight. Next week, we will talk about the stellar graveyard, the white dwarfs, neutron stars, and black holes. Then that'll be it for stars. We'll move on to galaxies. So look forward to seeing you. As always, make sure you like, comment, subscribe. Make sure you ask me questions if you have any. I'd be more than happy to answer them. So I will see you all next week.